So we did differentiation by first principle in 9B, but we also learned a quick rule for differentiating, which is this rule here, this rule for differentiating any functions. So unless the question asks you to differentiate by first principle, otherwise you use the rules. We also learned about tangents and normal last lesson. That's a tangent, that's a normal perpendicular to the tangent at the point of contact. So today, what we're going to do is to introduce a new notation. This notation, oh, what's that? dy over dx. So again, to understand this notation, we'll start with an introduction. So we're going to remind ourselves what we did last time is that we have to vary the h to make the point Q as close as we can to P, and then that becomes the secant, becomes the tangent. We're going to do that again today so that you understand where that notation coming from. Okay, so we've seen that animation. So we're going to consider the parabola again, y equal to x squared. We're going to find the gradient of the tangent at 3, 9 on the curve. Draw the secant PQ, okay. And then we're going to make Q1, Q2, Q3, Q4 as close as we can to the point P. Of course, this is not drawn to scale. So this is Q1, Q2, Q3, Q4, and I can't label that on a computer. I can, but yeah. All right, good. So these are the points. So what we're going to do is work out the y value for each. So we're going to relive that moment where calculus was discovered. So again, we're going to understand from the view from a slightly different perspective. 3.5 squared, use a calculator. Do not round, keep the whole thing. Do not round, keep the whole thing. So we're going to find the y value for each of the points. 9.0601, 3.101 square, and finally 9. Okay, so I encourage you to do on a calculator. I mean, I've already done on my calculator, so I'll just write it down very quickly. I'll give you about a minute or so. Okay, so as you can see, as x gets close to 3, y gets close to 9, right? So that's very clear from the numerical calculation, is that as x goes to 3, y goes to 9, as expected. All right, but that's not the point. We're going to find how does the gradient, what's the gradient, how does the gradient tend towards? Okay, so we're going to look at these 4 bits. Okay, so gradient of PQ1, which is the gradient of that secant, the first one, that secant there, the red line. Let's work out the gradient using the formula y2 minus y1. So you do 12.25, this one, the y value, minus the 9 over 3.5 minus the 3. However, I want you to do this. I want you to see it with your eyes. Rather than doing the fraction, I want to show the full working. There's a reason I asked you to do that. Because in order to understand this, you have to show every step. And there's a reason for me to do that before you write down 6.5. Hopefully you can do that. Show that intermediate step. There's a reason. There's a reason for that. And you'll see, oh, I see it now. Okay, so yeah. Next one, can you do the same for PQ2, PQ3, and PQ4? Good. Good, excellent. Okay, so we've got all 4, all 3, and then you have to work out. Let's do the work calculation. Okay, let's try this. First one. Next one is 9.61. Again, showing full working for a reason, which you will see very soon. But now, again, it is a very patient subject, because I remember when I go to the say something, I don't know, but that's the thing. You got to be very patient, but that's the way how the maths is written. I mean, people can rewrite the syllabus. You still have to be patient. I mean, you can show the application to the student. Yes, it's relevant. You will still be relevant today, last century, next century. Math will always be relevant. You'll be guaranteed. You can bet money on it. Actually, you don't even need to bet because it's real. It's true. It's the truth. Okay, so that will be 6.1. Can you finish the rest? 9 point. And when you see it before your eye, you get to feel maths. See, people who play music, you get to feel music, but maths, you can feel it too, in a different way, in a very different way. And some people say, oh, maths is very beautiful. But you only see the beauty when you get to experience it firsthand. So let's try to do that. Again, I'm showing. I know it gets a bit boring, but that's the way. You have to do it at some stage. And then if you see it with your own eye, you say, wow, wow, and it become mind-boggling. But it may not be mind-boggling for you, but it was mind-boggling for me. When I first learned it, I've just found it, oh my God, took me days, months, still don't understand. It's just so true, so unreal, yet true. All right, so as you can see, the 6.001 simply is, you did that differentiation by first principle is H is 0.5, right? H is 0.1, but we're not using H in this point, right? H is approaching 0, which is approaching 0. Therefore, the gradient of the tangent is approaching 6, right? Approaching 6, and the gradient of the tangent at 3 is 6. We'll know beyond doubt this is true. It's not even reasonable doubt, it's beyond doubt. It's not doubt anymore. Now watch this. It was 6.5, 6.1, 6.01, 6.001. Eventually becomes 6. Right, that's nothing new. What's important is this bit. What's important is this bit. Why is this bit important? That's why I could introduce the new notation to. Okay, hopefully you all have it in front of you. Notice that both the numerator and the denominator is approaching what? 0. It's getting smaller and smaller. But yet when you divide something very small, you still don't get small, you get 6. That's why it's called infinitesimal. Infinitely small calculus. See, infinitesimal calculus, we're studying the very small, right? We divide something very small by very small, somehow the ratio becomes 6. It's mind-boggling. Very small, infinitesimally small, and the ratio is 6. And you spend months, years, and then it's just that somehow you could just, it's very hard. I don't know. Some people find it hard, right? It's getting close to 0, but yet the ratio is 6. Anyway, so that introduces a very cool notation. So let's look at it in a different perspective, slightly different. So we have P x y. We have to use a new notation. Instead of using H, we're going to call it delta x. What does delta x mean? Change in x. Change in the x value. So delta x means this point is x, therefore x plus delta x instead of h, right? And the y, we go change in y. Y plus delta y. This gap is delta y, which means the rise over run. So the corner of Q is x plus delta x, comma, y plus delta y. And if you do rise over run, then the gap between them is delta y over delta x, right? So the gradient of PQ is delta y over delta x, which is simply the rise over run formula. Change in x, change in y over change in x. Very good. And we see earlier that the gradient of the tangent at P is the limit, as instead of h approaching 0, we have delta x approaching 0 of delta y over delta x. Of course, delta y also approaches 0, but in such a way, it becomes a limit. And the value of that limit is called dy over dx. And that notation, as I said earlier, Newton studied motion, that's the velocity, first derivative. Leibniz give rise to this notation. He's from Germany, he's a judge, he came up with this notation, which is much more intuitive because derivative, gradient of tangent is a gradient. dy over dx is more intuitive. And much of the mathematics notation we use more on this in maths, right? Whereas in physics, people who study physics will use more of that for velocity, acceleration, which you will learn later. So Newton applied to motion, but Leibniz see the value. It's like pure mathematics, like it's the value, it's the gradient, dy over dx. That's where that comes from. How do I say that? I think I've got something here. Oh, it's all written here. Oh, there it is. Sorry, dy dx is pronounced as dy dx. And if you look at the textbook, they say there's a subject called dy. The house price is very expensive there, but that's another point. Dy over dx. Never been there my whole life, but I'll go there one day. Yeah. Okay. I know that place exists. Okay. Now the notation. Oh, it's all written here. The notation is very clever because the derivative is a gradient. The gradient is a function, rise over run, and the notation preserves the intuition of fractions. But be very careful that dy dx is not a fraction. It is a value of the limit. So we can't really separate the dx and dy yet. So you can't just write dy. It's dy on dx. Yes. Hi. All right, let's continue. The small differences, delta x, delta y, and the infinitesimal differences, the x and dy, are the origin of the word differentiation. The symbol delta is the lowercase Greek letter delta standing for difference. If anyone's Greek, see, like that stands for difference. Okay, so we're going to do the same thing. Remember, before we have fx equal to x power n, f dash. I think that's due to Euler, that notation, the derivative, or maybe someone else, some French mathematician. But anyway, it's this thing. Now what we do is we have to write y equal to x power n, dy on dx. So this chapter, can you please accustom yourself to a new notation. It's very important that you need to know how to write it, how to interpret it. So this is what I want to do. Write that y equal, again, write 1 over 20 and do dy on dx. 1 over 20 times 5x power 4, which is cancel a quarter x power 4. X power 4 over 4. Now, I could do it in a different method, method 2, provided it is a constant, only constant. You don't have to separate the 20, just do it straight away. Watch this. 5x power 4, just ignore the 20 at the bottom. It works. I recommend you do it that way, but if you find it uncomfortable, do it that way. Okay? All right, let's do more. Maths is fun. Calculus is fun. dy on dx. So you got half times 6 x power 5. Remember, you bring the index down, subtract the index by 1. Same thing for the next one. Bring the 3 down, subtract the index by 1, which is 2. So you get 3x power 5 minus half x squared. Any question? Very easy, very straightforward. So now you know where the dy dx come from. Come from infinitesimally small differences, both the numerator and denominator. It is a gradient, dy on dx. Yes? I prefer dy on dx rather than f dash because it tells a better story. Because it is a stand for gradient. All right, we're going to do some math question as usual. We've got 3 more pages to go, and then we'll do chain rule tomorrow, which is very exciting. But today we'll just limit ourselves to this exercise, exercise 9D. All finished. Let's move on. Hurry up. Chain rule 9E. Worry about today, then tomorrow. Okay, let's look at this one. It's not an easy question. It's a bit different because it asks you to find the equation of tangent, not at a number, at a point t. At a point t, x equal to t, so not a number. So you do the same thing. So you do the usual. To find the gradient of the tangent, let's remind ourselves, tangent is this thing. You have to find the gradient, which is the dy on dx. So how do I do that? Dy on dx equal 2x plus 1. That's your first step. Then we have to find the gradient of the tangent. Notice that I switch notation. That's the derivative, not the gradient of the tangent yet. It's the gradient function. Once I substitute the t in, it becomes a gradient. We have to know the difference between them. People just use them, which is wrong. T. Does it make sense? So once you know, once you have substituted, it becomes a gradient, it becomes a value, not a function, right? Although t can vary, it's a polynomial, but it's different from the x. Okay, so we've got the gradient, and then we have to find the point. The point is x1 comma y1. How do I get x1? We've already got t. That's your x1. What's the y? How do I get the y value? What do we do? Anyone? That's it. You substitute t in there. Well done. I didn't even see you there today. That means you've changed. That's good. Excellent. Otherwise, I would have moved someone, but that's not necessary at this stage. Good. Excellent. Right? So now we've got x1, y1. Let's do it. Again, the algebra can get a bit tricky, but we try our best. So we do y minus y1 equal to mt x minus x1. Right? Be sure. I think that's the high. Oh, I can go higher. That's it. That's better now. Okay, good. So we do y minus. Now, because the y value has more than one term, I will use a bracket. Otherwise, you get wrong, particularly when there's a negative. Equal to gradient. What was the gradient? Again, you need another bracket because there's two terms. 2t plus 1. X minus t. Hopefully it's okay. Got it? Go slowly. Now, expand. Now, when you expand, be very careful. This is a gradient. Do not expand in full, if that makes sense. The other one, you can expand. Right? Be careful with t and plus. That's a t. Okay. So do not expand the x because that's one gradient. Otherwise, it gets tricky. The other one, you need to expand and collect like terms. So you get negative 2t squared minus t. It's an unusual type of question that you don't, it's not unusual, but it's something you don't normally see. But once you see it, oh, okay, pretty straightforward. And then you move things to the other side. And then make sure you move this whole package, this guy, the negative become positive. Be careful with t and plus. They look very similar, so make sure you write t clearly. And collect like terms. So some terms gets killed. This guy, good. Some term doesn't, so just be careful. So you end up with minus t squared and plus 1. I think that's right. Good, I got it right. I've got my answers to double check. Right? So the gradient, remember, the gradient, do not take it apart. It's meant to get together. That's your gradient. Right? So it's like gradient intercept form, right? Y equal to mx plus b. Your b is negative t squared plus 1. And that's required for the second part. That's required for the second part, for part B. This is a hard question. You may get that in your exam. Not exactly the same, of course. You may get something similar. Watch this, how maths people solve the problem. Let's find the equation of the tangents to the curve passing through the origin and the corresponding point of contact to each tangent. Okay, when you read it once, makes no sense. Read it again, gives you some impression. Okay, read it again. Hence, find the equation of tangents to the curve passing through the origin and find the corresponding point of contact. Okay, when you read it again, you get a better picture. Let's see what that means. There's the parabola drawn for you. This is the graph of y equal to x squared plus x plus 1. Next bit, we're going to draw tangent. Now, obviously, not all tangent pass through the origin, right? Some don't pass through the origin. Which one? Which tangent pass through the origin? Now, because we've got that equation of tangent at any point, that t could be anything, it allows us to adjust. T could be anywhere, right? I just make sure the y-intercept is 0. So you make sure the y-intercept is 0, then the tangent will pass through the origin. Passes through origin. Algebra is very powerful. It allows us to assume that we know the answer and then work backwards rather than guess and check. It's amazing. And the next important invention is calculus. Allow us to find the rate of change. It's just, yeah, it's very powerful stuff. Maths is amazing. I don't know. I don't know, but that's not an amazing subject, but maths does a lot of things. It's really good. Okay, so we're going to solve it. Oh, how do I solve? Move the t squared to the other side. And we square root. What do we do when we square root? Ah, very nice. What's square root 1? 1. Okay. But have we answered the question? Not yet, but we're very, very close. We need to find the point of find the equation of tangent. Okay. So where t equal to 1, t equal to -1, I get 2 equations of tangent. Watch this. The first one, t equal to 1, will be y equal to 2 times 1 plus 1. You substitute 1 into the formula. And obviously, the y-intercept will become 0. Will become 0. Right? So that becomes, remember, square root 1, not the negative. So that gets killed, so you get 3x. Y equal to 3x. Passes through the origin. What if t is -1? Works the same thing. 2 times -1 plus 1 x minus -1 square. You will still get cancelled. You get 0. So you get y equal to x. Wow. Oh no, y equal to -x. Oops. Okay. What does the picture look like? So we've got the 2 equations of tangent that pass through the origin. And at what point? Well, remember the point of contact was t comma t squared plus t plus 1. So the t is the x value. So the 2 point of contact is 1 comma 3, right? If you substitute 1 in there, or 1 comma -1 square minus 1 plus 1. If you do your calculation, it becomes 1, 1, 1. So 1, 3, 1, 1. Yes. So 1, 1 is here. Oh, hang on. Is it? Oh, negative. Sorry about that. Negative. It now makes sense. -1, 1. Here. That parabola is wrong to scale. I use the computer. The other one is 1, 3. 1, 3. That's 3? Okay. That's a 3. So if you draw the tangent, well, if you draw the origin, seriously, it will become a tangent. I've got the tool. It's not like my ruler. Watch this. It's very cool. I do. Watch this. It's pretty cool. Look, that tangent. The other guy is a different color, red. Look at this. It's a tangent. Now, not finished yet. You just have to bear with me. See, it's a tangent. The other one is a tangent. Cool. They all pass through the origin, and there's exactly 2 tangents pass through the origin. How cool is that? Maths is cool. Allow us to solve, and calculus is cool. It can solve so many problems. Maths is invented. Oh, what's the thing? Necessity is mother of invention. Some people say, oh, who invented maths because they really hate maths? Some students say, yeah, because you don't see the relevance yet. But once you see the relevance, oh my God, yeah. I think it's the oldest subject of the whole world. And if you look at all cultures, even indigenous cultures, they got their own, maths, they got their own numerical system. Like, it's necessity. Like, how are you going to live without numbers, without mathematical thinking? And, oh my God, it's almost impossible. Oh, before I continue, there's a thing we just mentioned. Okay, There's a word starts with P. What do we call this? We met this earlier in the function topic. Forgot. Parametric equations. And the T is called the parameter because it allows us to express both the x and the y with the same pronumeral. So if I know T, I know both x and y, the parametric equations. Okay, which you will meet more of that different example later on. These are all really cool ideas in maths. They're all algebra, but they're subtly different. Okay, we've got 2 more pages that we're done. Yes, mark the roll. I'm going to mark the roll soon. No. All right, let's continue. Next page. All right, we're going to look at second and higher derivatives. The derivative of a function is another function so that it can be differentiated to give the second derivative of the original function. So if you can differentiate it once, you can also differentiate it again. But the question is, what's the notation? Break. That's good. Continue. Second derivative. So what's the notation? Well, I just have to show you how it works. First one. So that's this one, right? F dash is the first derivative. If you dash it again, double dash is the second derivative. So they're like easy, right? Double dash is to differentiate twice, right? And now I could differentiate one more time, third. But then it gets like a bit annoying where the number, you actually start counting the number of dashes. So after 3 dash, we say, let's use a number. That's it. It's like square, cube, power 4. You know what I mean? You know what I mean? Like you just have to, you can't just keep inventing a term, right? You can write x power 2, but you say x squared, x power 3, x cubed, but when it gets to the fourth one, you say x power 4. There's no special name for it, right? Same idea. Okay, so how about this one? dy dx, exactly the same thing. Now, oh, it looks a bit not very symmetrical. Why do we put the 2 on the d and the square of x? It doesn't look symmetrical. Let me show you why. Let me show you why. Why you add an extra d on dx, right? So every time we differentiate it, we do an extra d on dx. So if I could do that extra, actually wrong color. dy on dx, and then we're going to apply the d. Can you see that how the logic works? If you see how the logic works, you'll see why the notation is like that. I don't write the y again. It's d on dx on the y. So on d on dx on this thing, which becomes, see the d got double, so d squared. And then well, we don't write the bracket dx, right? We just write dx squared, if that makes sense. Hopefully, so we don't use the bracket, so that's where that comes from. So if I want to get to the third derivative, actually before I do that, you get 12x squared plus 30x. If I get to the third derivative, you get the 3y dx cubed. Got the idea? 24x plus 30, and one more, the 4y dx power 4. And it's consistent. We don't like see dash notation, you start to think, oh my god, I need to start using numbers. But that is consistent. All right, okay, so just like the first derivative is the gradient function of fx, the second derivative is the gradient function of the gradient function. What does that mean? Next, you will interpret the second derivative in terms of the concavity. But there are no simple geometric interpretation of the high derivatives. So derivative, the first derivative tells us about the gradient, second derivative tells us about the concavity, which we'll discuss next week. But now, we just need to concern ourselves with how do I differentiate it, how do I find the gradient, how to find the equation of the tangent, equation of normal. All right, now another notation, the operator notation. So notice that I have to write them in two separate lines. It's like doing these sort of things. Again, necessity another mother of invention. So let's say we see this, y equal to x squared, right? So if I got x equal to 1, y equal to 1 squared. And they'll say, oh my God, mathematician, that's just too much. Which is got fx equal to x squared, we'll link it in one sentence, right? And the same thing with derivative. How does it work? We can join that under one statement. We can join these two together. It's like conjunction, right? In English, like you join the two sentences together using and or whatever. But now watch this. dy on dx. We have no doubt that 2x, right? X squared is 2x, right? And then what if that I change the y into x squared? Well, you can do that. And the new notation is born. That d on dx means differentiate. That thing is like a verb, differentiate. Differentiate, it is that's a function whose domain range are the set of functions. So if I go to express this, differentiate a function gives you a function, another function. So you can go function differentiate d on dx, you get another function. We call that the derivative, right? It's like with the function notation, if I go fx is x squared, I map 1 to 2, 1, 2 to 4. Make sense? This is the operator notation of function. So math is very flexible. Like there's function on mapping numbers to numbers. There's also function that map function to function. It's very flexible. And for your FYI, this thing is called, guess what? It's very intuitive, primitive, right? Oh, right? So this is the derivative. When you go backward, it's called the primitive. Again, that was not in your textbook yet. It's next year's textbook. Actually, maybe it's on the next page. But anyway, any question? And maths is like people solve equation. There's inverse preparation. Like there's plus minus. If you add something, how do I undo plus? I undo by minus. How do I times? How do I undo the times? I undo the times by divide. So the next question is, if I could differentiate, how do I undifferentiate? That's what we're going to do now, right? We're going to, that's why maths is fun. We'll go forward, let's go backwards. And some of you do chemistry, there's what we call that, redox equation, whatever it's called. They go forward, what's that called, reaction? We can go backwards, I don't know. I learned that in 11, I forgot, long time ago, but that's fine. We'll do the same thing. We'll do exactly the same thing. Find the derivative of the following. Watch this. Watch. You want to move? You don't want to move. Good. Stay there. Y, dy on dx. I mean, you can still use the y dash, but it just looks cooler. Dy on dx. 3x squared plus 0, right? The 1 disappears. Dy on dx. 3x squared. Dy on dx. Also 3x squared. And the question is, if I give you the derivative, what's the original function? Well, obviously, is it this guy? Yes. Is it this guy? They all have the same answer. So which one do I write? And unlimited more, right? I have to write y equal to x cubed plus a constant. It's undetermined. We don't know. Could be 1, could be -3, could be 0. Does that make sense? Now, if I differentiate that, where c is a constant, we get that. And the next question is, what if I change to something different? What's y? We want to have a try. What differentiate give you x power 4? And if you do some experiments, on a scrap paper, oh, must be x power 5, right? But if I differentiate it, I got that annoying 5 in front of me. How do I get rid of it? X, yeah, just put a 1/5 in front. So it must be 1/5 x power 5, right? Necessity is mother of invention. But wait, plus c. Now, we're not concerned with our formula yet. This is called topic of integration. Some of you asked me already, which will be studied in year 12. Reverse process. So when we differentiate d on dx, to get the primitive, oh, sorry. Oh my God, the other way around. So if I differentiate the primitive, I get the derivative, yes? And if I Go backwards is called integration. And so, not surprisingly, has a dx integral. We learned that next year. So you go, yeah. And again, that notation also due to Leibniz. He expresses so that it looks more common sense, more intuitive. Again, you learned that next year. There's plenty of YouTube. You can watch it if you can't wait. Not available during my days, but it's available to you now. But you don't need to do that. Okay, so let's write down some of these. So this is x, right? This is x squared on 2, x cubed over 3, right? And we'll just go x power 4 over 4, x power 5 over 5, right? Now, we're not concerned with the formula yet. Don't try to, let's try to learn formula. No. I want you to use this to use the table above to do that. That's in the question in the textbook, yep. This one, not, technically speaking, you do. But you see why. Let me show you why. Let me show you. To answer your question, we're going to do this first. Watch this. Look at that, x squared. This one, right? Okay, x cubed over 3. That x squared becomes x cubed over 3. And then sine times by the 9. Yes? And then the 5, using this 1, becomes x. Just remember there's a 1 next to the 5, becomes x. And then we'll just need 1c. It will be annoying to do a plus c for every object. If that makes sense, hopefully that answers Sam's question. Why don't we plus a c? That's just a table for us to refer to it, so that you can do the question. Now, normally when you do a question, you do plus c at the end, but not for like, it's just annoying, right? To write that plus c for each time. No, you just do plus c, 1 plus c at the end. Yep. Okay. Good. So let's simplify that. That will be 3x cubed minus 5x plus c. And how about this guy? Have a try. Use the table. X cubed, x power 4. So now I just want you to use the table to do it. Don't try to learn the formula because it will confuse you, because you're just differentiating. Don't go backwards yet. It's like when you try to ride a bicycle. Oh, let's ride a bicycle. You haven't learned how to ride it, you start going backwards. It's just too dangerous. Yeah. All right, what's the other one? 6. X, it will be x power square over 2 plus c. So the answer is that. I think that's the last thing we will say. All right, any question? Now, why is tomorrow exciting? Tomorrow, you're going to learn how to, I'll give you the booklet tomorrow. How do I differentiate this guy? Like this, like very big. Oh, do I have to expand? You find out tomorrow. But for now, can you just get used to the notation? Maths is exciting. Every day you learn something new, completely new. And then after the, all right, that's good. It's not high as well. Good. All right.